In this video, I'm going to introduce you to oxidation-reduction reactions, also known as redox reactions. We'll look at some of the terminology and then how to actually write and balance an entire redox equation. Electrochemistry is just looking at how chemical energy can be changed into electrical energy. So when we have these electron transfer reactions, we call them oxidation reduction reactions or redox reactions. Basically, any electrochemical process here that results in the generation of electricity or a reaction that can be caused by kind of imposing an electric current on it is going to be a redox reaction here. So we're either going to generate some form of electricity or we're going to use some form of electricity to cause a reaction to happen here. And that's what you would expect for a redox reaction or an oxidation reduction reaction. Oxidation number is just referring to the charge on an atom. So if you ever see anything in an AP question about what is the oxidation number of this element or atom, they're just asking for the charge here. All right, so don't be confused by that. You just need to realize oxidation number means charge. Now, we definitely need to understand what oxidation and reduction are here. These definitions are huge. You might be asked to identify the oxidation and reduction taking place in a reaction, or which substance is being oxidized or reduced. So we need to understand this. Oxidation is when you have a loss of electrons. So our electrons are being lost. So if you're losing negatives, you're going to be essentially turning positive here, okay? And then reduction is when electrons are gained. So if you're gaining electrons, you're going to be becoming negative. Oxidation, loss of electrons; reduction, gaining of electrons here. And these are two big terms that you really need to make sure you know and understand. If we are looking at this reaction taking place here, you can see that the reaction has Cu2 plus and magnesium becoming Cu and Mg2 plus. So if you notice here, the magnesium on the reactant side is just regular solid magnesium. It would have no charge. But then on the product side, it's becoming magnesium 2 plus. So if you notice, it lost electrons. It went from 0 to 2 plus. Electrons were lost. So oxidation would be taking place in the magnesium. But then the copper, on the other hand, goes from 2 plus to regular solid copper, which would have a charge of 0. So this would be a gaining of electrons. 2 plus gained electrons and ended up with a charge of 0, essentially. So this would be reduction. Oxidation is loss of electrons. Reduction is gaining of electrons. This is the way I learned the difference between the two. It's still something I use today when I have to figure out, what's oxidation and what's reduction. It's Leo the lion goes grrr. So Leo stands for loss of electrons. That's oxidation. The grrr part, the gaining of electrons, stands for reduction. Okay? So Leo is loss of electrons, oxidation. Gaining of electrons is reduction. And this is just a neat little trick to help you remember the two terms because they are that important and you need to understand what each of them means. If you don't like Leo the lion goes grr, you could use oil rig. All right, this is another one here that you could use to help you remember. Oxidation is loss of electrons, so you can use oil for that, or reduction is gaining of electrons. You can use the rig part for that. So oil rig, Leo the lion goes grr, whatever you need to use, you just need to know that oxidation means loss of electrons. So if electrons are being lost, you're going to be positive, and reduction is gaining of electrons, and that's going to be negative here. I just want to introduce you to two other terms here. These are not as big of a deal anymore. AP has kind of backed away from them a little bit, but you should be aware of them. If you're asked about the oxidizing agent, this would be the one that accepts the electrons. So basically, it's the species that is reduced. So it's kind of opposite of what you think here. If you're talking about the oxidizing agent, you're talking about the one that is reduced. Essentially, an agent here is like facilitating or helping with something, like a travel agent. So the oxidizing agent is the one that is reduced. And then the reducing agent is the electron donor or the species that is oxidized here. Okay, so just be aware they're kind of opposite. If you're looking for the reducing agent, you're looking for the one that is oxidized. And if you're looking for the oxidizing agent, you're looking for the one that is reduced. Again, not as big of a focus anymore, but if you see these terms, you need to understand that pretty much you're looking at the opposite here, understand what they mean. We want to be able to understand this on a molecular level here as well. So if you see in this picture, we are taking a piece of zinc metal, we're putting it in a solution with copper 2 plus ions. So we really want to see what's taking place. So the reaction is here at the bottom. You have solid zinc reacting with Cu2 plus ions, becoming zinc 2 plus ions, and solid copper. All right, so if you look at the picture here, these atoms here would be your solid zinc atoms from the strip of the zinc, and then these little blue ions are your Cu2 plus ions that are in the solution. What's actually happening here is the solid zinc is undergoing oxidation. The solid zinc is losing electrons, okay? Those electrons essentially are going to the Cu2 plus ions in the solution. So as the zinc loses electrons, it forms Zn2 plus, and you can see here the Zn2 plus is now entering the solution, but those Cu2 plus ions now are gaining those electrons, okay? This is reduction now. So the Cu2 plus ions gain those electrons, forming solid copper. And if you notice, the solid copper atoms start to plate on the zinc. So you can actually look at this picture here. If you compare the two, you can see the solid copper forming on the strip of zinc. But the zinc is slowly disappearing. Essentially, it is losing electrons and entering the solution, and the copper 2 plus ions are gaining electrons and plating out. All right, so you can see oxidation and reduction taking place here on a molecular level, and you definitely need to understand this on a molecular level. Very important to understand that oxidation and reduction go together here. If you have one, you will have the other as well. You can't have oxidation without having reduction take place. You can't have two oxidations or two reductions in the same equation. It doesn't work that way. All right, so if you have one in the equation, you're going to have the other existing as well. So we can write these as what we call two half reactions. All right, half reactions are essentially where you would write the reaction involving oxidation, and then the one involving the reduction. So if we look at this example here, this is the overall equation. 2 magnesium solid plus O2 gas is going to form 2 magnesium oxides here, and they're solid as well. So we want to look at the oxidation and the reduction half reactions here. Essentially, the magnesium, which would have a charge of 0 in the solid form, all right, is becoming magnesium 2 plus on the product side. If you notice, it's MgO, but think about this. It would be Mg would have the 2 plus, and the O in that compound would be 2 minus. So it's going from a charge of 0 to a charge of 2 plus. Well, that's loss of electrons. All right, the magnesium lost electrons, and you can see the electrons here on the product side. Well, that's oxidation. Loss of electrons is oxidation. The oxygen, on the other hand, here, it's going from a charge of 0 on the reactant side. O2 gas is a diatonic, it has no charge. All right, but then on the product side, it's becoming 2 minus in the formula for the compound. So it is gaining electrons. It went from 0 to 2 minus. That's gaining electrons. That's reduction. So this would be the oxidation half reaction. This would be the reduction half reaction. The oxidation is when the electrons are being lost. The reduction is when the electrons are being gained. And then here's the overall equation that has the oxidation and the reduction in it. Remember, you can't have one in a reaction without the other here. Let's talk a little bit more about these oxidation numbers. Remember, oxidation numbers are just the charge on an atom. So there's some things you need to realize here. Some of this you already know from, previous content, but some of it might be new here. Sometimes you have to be able to look at an atom and determine its charge. Well, obviously here, we kind of already saw this, but elements that are not bonded to another element are going to have an oxidation number of 0. So these would be like your pure solids, like your sodiums and irons, okay? Your magnesium, if it's just a regular element by itself, that's going to have an oxidation number of 0 or no charge. Same thing for your diatomics, O2, N2, so on. They just have no charge. So their overall charge would be 0. If you have a monatomic ion, the oxidation number is just equal to the charge on that ion. So if you have lithium 1 plus, the oxidation number is 1 plus. Plus, if you add iron 3 plus, the charge, the oxidation number is 3 plus, and so on. All right. The oxidation number of oxygen is usually 2 minus. You know this. If you look up oxygen on the periodic table, it's in the 2 minus column. So typically, oxygen has a charge of 2 minus. However, you need to understand that if you have hydrogen peroxide or O2 2 minus, its charge is 1 minus. All right, so that's kind of a little different. This is definitely something new. Typically, oxygen is going to have a charge of 2 minus in a compound, all right, as long as it's not O2, which would be 0. But typically, it's going to be 2 minus unless it's involved with hydrogen peroxide or the peroxide ion here, then it's going to be just 1 minus. This is something you have to know. The oxidation number of hydrogen is usually 1 plus. We know this. Hydrogen is in that same column here as the alkali metals. So he's typically 1 plus, except when hydrogen is bonded to other metals here in compounds, then it's going to be 1 minus. So for example, if you had CaH2 or LiH, then the hydrogen would be 1 minus there, but typically it's going to be 1 plus. For the fifth kind of rule here, it says that group 1A metals are always 1 plus, 2A are always 2 plus. We pretty much know this. You know which columns have which charge on the periodic table, so that's not anything new. And then the last part here is the oxidation numbers of a molecule must add up to 0 if the molecule has no charge, or it needs to add up to the charge on the ion itself. So let's look at an example here. Let's do HCO3 minus. So what you would do here is you start assigning charges to the ones that you know. Well, we already know that hydrogen is going to have a 1 plus charge unless it's kind of bonded to these metals here, which it's not. So we know that the charge here on the hydrogen is going to be 1 plus. All right. Well, we also know the charge of oxygen is typically 2 minus unless it is with, hydrogen peroxide or peroxide here, which would be 1 minus. So oxygen is going to be 2 minus, right? Then we can figure out the charge of the carbon here. Well, if you notice, you have to be careful here because there are 3 oxygens, okay? So if each oxygen is 2 minus and there are 3 of them, you have a total here of 6 minus alone from your oxygen, all right? But the hydrogen has a 1 plus charge, so you might say, okay, well, 6 minus and 1 plus, that brings me to 5 minus, but don't forget, the charge here on this particular ion is minus, all right? So the charge on the carbon is going to be affected by that. So right now, we have 5 minus in this case, total, but we need the charge on the carbon to kind of balance everything out here. All right, so be careful. We have 6 minus just from the oxygen, but there has to be a minus charge on the compound. All right, we already know that hydrogen is 1 plus. That brings us to 5 minus, but you need there to be a 1 minus charge here. So that's going to make the carbon 4 plus. All right, so you could quickly figure out the oxidation numbers here of every element in a compound, kind of using the ones you know, and then going from there. So if we total this up right now, be careful. We have 6 minus from the oxygens. Now we have a total of 5 plus from the hydrogen and the carbon. So 6 minus 5 plus gives us 1 minus left over, which is the charge of this molecule itself. All right, so you need to use these rules to be able to figure out oxidation numbers or charges here of elements in a compound. And this is definitely something you will have to do. So you need to know these rules. This is just showing you some of those common charges that you should be aware of. We already know that certain columns on the periodic table have certain charges or oxidation numbers. So this really isn't anything new. You can see some examples here, but we are going to try this for H2SO4, sulfuric acid. So the first thing you want to do is pick out the charges that you know. So I know the oxidation number of hydrogen is going to be 1 plus, and the oxidation number of oxygen is going to be 2 minus. But realize here there are 2 hydrogens, so that's going to be a total of 2 plus from the hydrogen. There are 4 oxygens, so that's going to be 8 minus from the oxygens. So when I look at this, I have 2 plus, 8 minus, 1 element left here to balance this out. This molecule has no charge on it itself, so that must mean that the sulfur must be 6 plus. All right, because the 2 plus from all the hydrogens, 6 plus from the sulfur now gives us 8 plus, which balances out the 8 minus from the oxygens, giving us an overall charge of 0. So that's what you'll have to do here. For any example, pick out the charges you know, and then go from there to figure out the ones you don't know, but realize they should add up to the overall charge on the molecule. And you should be able to do this for any molecule I give you following those rules. For each of these examples, we want to identify which substance is being oxidized and which is being reduced in these equations here. So essentially, you need to use oxidation numbers to be able to figure this out. So if we look at the first example here, I see calcium solid as my first substance. You should realize that's just essentially a pure element here. So that would have an oxidation number of 0. I then see O2 gas. Well, that's a diatomic. That's pure substance, oxidation number of 0. And then I see CaO on the product side. You need to realize that is a compound, so you can figure out the charges here. Obviously, we know that the charge of calcium from the table is 2 plus, and oxygen is obviously 2 minus here from our table. So if we look at this, I can see in my reaction, calcium went from 0 to 2 plus. So that's a loss of electrons. Calcium lost electrons, so the calcium is the one being oxidized. And then the oxygen went from 0 to 2 minus. That's gaining electrons. So the oxygen is the one being reduced here. All right. So you need to be able to pick out the substances that are being oxidized and reduced based on the oxidation numbers here. So let's look at the next example. All right. You can see it looks like there's more going on here, but again, pay attention to oxidation numbers. I see magnesium solid on the reactant side. Well, that's a charge of 0. Then I see a compound. So HCl, these guys are going to have charges. Well, H from the table is going to be just 1 plus. Cl here is going to be 1 minus. All right, now when I go to my product side, MgCl2, well, it's a compound, so magnesium is going to be 2 plus from the table. Chlorine here is going to be 1 minus, all right, from the table. And then the H2 is a diatomic, so it's going to be 0. So you might say, wait, we have 3 substances here. How can we have oxidation and reduction with 3 substances if there can only be 1 oxidized and 1 reduced? Well, if you look at this, all right, the chlorine has the same charge on both sides. So the chlorine is not oxidized or reduced. The magnesium, on the other hand, goes from 0 to 2 plus. That's a loss of electrons. So that's going to be the oxidation here. All right. And then the hydrogen goes from 1 plus to 0. That's gaining electrons. So the hydrogen, all right, is the one that's reduced, not the chlorine here. Make sure we understand that. It's the hydrogen. And the chlorine just is 1 minus to 1 minus, so there's nothing going on with that one. All right, so I would say right now, pause the video, try the last one on your own, and see what you come up with. Pause the video right now. All right, hopefully this is the answer you got here. The sodium is being oxidized, the loss of electrons, and the hydrogen is being reduced here, the gaining of electrons. So you have to be careful. I would rewrite water as HOH so that you can see that it's the hydrogen itself in the water that is being reduced. All right, so you definitely need to be able to determine which substance is oxidized and reduced in a reaction using these oxidation numbers. I'm going to give you some basic steps for writing a redox reaction here, but realize we are going to, do a full redox reaction with balancing coming up. This is just writing a general redox reaction. So first, we want net ionic equation. We don't want the substances, the ions here that maybe aren't involved in the overall net ionic part of the equation here. We can assign oxidation numbers and then determine what is being oxidized and what is being reduced. So you notice in this example, it says lead foil is immersed in silver nitrate. The nitrate part is not going to be important. If you notice, we have our lead, we have our silver 1 plus ion written, but then for our products, we just have Pb2 plus and solid silver here. Essentially, the nitrate would cancel out from both sides. So we got our net ionic equation here. I have the charges already assigned. So if you notice, the solid lead here is going to be 0, 1 plus for the silver, 2 plus for the Pb2 plus, and then obviously solid silver here is going to be 0. So if we look at this here, if we follow the charge, we can see the lead goes from 0 to 2 plus. That's loss of electrons here. So the Pb is going to be oxidized, all right, or oxidation taking place here. And then we see the silver, right, going from plus to 0. Well, that means it gained a negative or gaining electrons here. So the silver is your reduction. All right. So definitely understand oxidation and reduction here. Be able to look at a reaction, look at the oxidation numbers, and determine where oxidation is taking place and where reduction is taking place. Here are the steps for balancing a redox reaction. So you definitely need to get to a point where you know all of these steps off the top of your head. You need to know exactly what you need to do to balance one of these redox reactions, all right? I'll walk you through the steps first, and then I'll show you how this applies to an example, and then we'll do some more examples. So the first thing you do for a redox reaction here that you have to balance is you write the individual half reactions. So you'll write your oxidation, you'll write your reduction half reactions. Then you balance any elements in those half reactions that are not hydrogens and oxygens. So any elements that need to be balanced in those half reactions you would balance, but not hydrogens and oxygens. Then the third step, we would use water to balance the oxygens. And then once all the oxygens are balanced in both, we use H plus to now balance all our hydrogens, all right? Water balances the oxygens first, and then H plus balances any hydrogens. Then we have to use electrons here in each to balance the charge for each half reaction. And I'll show you what this looks like, okay? Then you need to get a common multiple here for your electrons in order for them to cancel. So you multiply each reaction by a number in order to cancel out your electrons. And then you will just cancel and add up your half reactions here. The electrons must cancel out. And then we can actually verify that we have the right overall number of atoms here on both sides and so on, right? So that would be the basic steps of how you do a redox reaction. But then there's one more step here that you would need to do if it says that this is taking place in basic solutions. So if you're told this is taking place in basic solutions, you'd have to add OH minus to both sides for every H plus in your final equation. So if you had 4H plus on one side of your equation, you would have to add 4 OH minus to both sides of the equation. And on the one side with the H plus, it would make water. I'll show you what all this looks like. I'll show you each step here. But the key is you need to get to a point where you know these steps off the top of your head and you can just do them in a redox kind of problem here where you're just balancing a redox reaction. So you really need to study these and just be able to know them right off the top of your head. Let's look at our first example here. This says write the balanced equation for the oxidation of Fe2 plus to Fe3 plus by Cr2O72 minus to Cr3 plus in acidic solution. All right, so the first step is you write your half reactions. Well, they basically told us the half reactions in this example. We have Fe2 plus going to Fe3 plus, all right? And then we have the Cr2O72 minus going to Cr3 plus. So that's step 1, write the half reactions, which is what we did. Step 2 says balance any elements that are not hydrogen or oxygen in each of these half reactions. So if you notice in the first half reaction, it's just iron, and there's only one iron on each side of the equation, so we don't have to worry about that. But then in the second one, we're ignoring the oxygen yet. Hydrogens and oxygens we ignore. It's just anything other than hydrogen or oxygen. I see 2 chromium on my reactant side. Only 1 was on the product side, so I put a 2 in front. So I balanced the elements that were not hydrogens and oxygens in step 2. So now I'm done with that. I'm ready to move on to step 3. Step 3 says, first, you use water to balance any oxygens that are present. Well, if you notice in the first half reaction, there's no oxygens, so I don't need to worry about that. But in the second half reaction, I have 7 oxygen here on the left side. So that means to balance the oxygen, I need 7 water on the right side. So now if you actually looked at your oxygens on both sides, there would be 7 on each side. So we use water to balance the oxygens. But now we have to use H plus to balance any hydrogens. But you must do the oxygens first, like we did, and then you do the hydrogens with H plus. So again, the top half reaction has no hydrogen in it, so we don't need to worry about it. But then when we get to the second half reaction, we have 14 hydrogen on the product side. So that means I need 14H plus on the reactant side for that one. All right, so we just completed step 3, which said use water to balance your oxygens, and then you use H plus to balance any hydrogens. Now we're ready to move on to step 4. Step 4 says you're going to use electrons here to balance the charge. All right, so if you look at each half reaction individually now, if we look at the top half reaction, we have Fe2 plus going to 3 plus here. So 2 plus to 3 plus. So we lost 1 electron, okay? We lost 1 electron, so we put on the product side here 1E minus. Essentially now, if you total up the charge on both sides, it should be equal. It doesn't have to equal 0, it just must be equal on both sides. So 2 plus on the left side, you have 3 plus plus your 1 minus is now 2 plus. All right, so the charge matches on both sides here of this half reaction. Now we're ready to do the second half reaction, which is a little bit more involved. There's a lot more charges, but just kind of an FYI here, if you added electrons to the product side of your first half reaction, the other half reaction is going to have the electrons on the reactant side. That's just the way it is, all right? The electrons will be on opposite sides here in each, all right? So you definitely need to be aware of that. You would never have the electrons both on the same side for each. So now when we do the second one here, I can see I have 14 H plus, so that's 14 positive alone just from the hydrogen. And then for the Cr2O7, that's 2 minus. So my overall charge on this side, 14 plus 2 minus, well, that's 12 plus. All right, so I have 12 plus here on the left side. On the right side of this one, I have Cr3 plus, but I have 2 of them. Be careful. So this is a total of 6 plus. The water has no charge. So I have 12 plus going to 6 plus. All right, I need them to match. All right, realize here, if you added the electrons to this side, that would not make them match. That would just make this charge get closer and closer essentially to 0 before you go negative. So I have 12 plus going to 6 plus. I need to add 6 negatives or 6 electrons to the left side. Right now, if you total that up, your 12 plus that were here plus the 6 minus becomes 6 plus. And this side we said was 6 plus. So 6 plus going to 6 plus. Boom, you're good. Okay? The charges don't have to be equal to 0. They just need to be balanced on both sides of your half reaction. Okay? So 2 plus now by adding the 1 electron. 6 plus now by adding the 6 electrons to the reactant side. So that's how you got to do this. You have to use the electrons to balance the charge, and you need to be careful. You need to total up these charges correctly on each side, or it will mess up your equations here. Step 5 says you need to get a common multiple here in order for the electrons to cancel out. Well, that's pretty easy. If we had 6 electrons in the second one and 1 originally up here in the first one, the way they would cancel out is if you just multiply the first one by 6. Okay? So if I multiply this first half reaction by 6, everything gets multiplied by 6. So now I have 6 Fe2 plus, 6 Fe3 plus, and 6 electrons. You're not just multiplying the electrons here, you would multiply the entire half reaction by the number in order to make the electrons cancel. You might have to multiply both sometimes by a number, but in this case we lucked out. Only one needed to be multiplied by a number. But now my electrons would cancel out. So I'm ready to move on to step 6. For step 6, you basically have to cancel out your electrons, combine anything else, cancel anything else that might cancel out here. You never know. You might have waters that could combine in each half reaction, H pluses, you never know. So you have to check each and then total it all up to get your new kind of balanced equation here. So my electrons canceled. That was the point. 6 minus on the top right and 6 minus on the bottom left. They cancel. Nothing else cancels. So I just add these up. Anything on the left side of the arrow stays on the left side. Anything on the right side stays on the right side. And you can check this to see if you're right. For example, I see here that I have 14 hydrogens on the left side. And when I look for all the hydrogens on the right, I do see 14 hydrogens, and so on. You can check every single element. You can make sure your charge is balanced. All right, that's how you know that you did this right. So essentially here, this is an acidic solution, so I don't have to do step 7 for this one, but I will show you an example of what step 7 looks like. So now we went through every single step so you could see what you would do for each of those steps. But you got to get to a point where you can memorize those steps so you know exactly what to do for one of these balancing of a redox reaction. Now we're ready to try another example here. We want to balance this equation, but it's going to be in basic solution. So that's going to be important here. We will need to do the last step, step 7, but we'll worry about that at the end. So we're ready to follow our steps for balancing a redox reaction here. The first step is you write your half reactions. So you might just see at first like, whoa, I have one equation here. So you have to just pick out the half reactions. And it's quite easy. You just pick one of the substances. So I'll say I'll pick the Cl O3 minus here. And you might say, well, which substance is that going to be in the half reaction with? Well, think about it. It's got to have something with Cl in it. So that's going to be with the Cl2 here on the product side. And then you pick out the other substance, the SO2, and that would be in the half reaction with the SO4 2 minus. All right, so I wrote my half reactions. That was step 1. Step 2 says balance anything that's not hydrogen or oxygen. So in the first half reaction, I have 2 chlorine on the right, so I need 2 chlorine on the left. In the second half reaction, I see sulfur, but it's balanced on both sides. So now I'm on step 3. I'm going to use water here to balance the oxygens first. So I see 6 oxygen on the left of the top half reaction. So I'm going to need here 6 water on the product side. And then when I look at the second half reaction here, I see 2 oxygen on the left, 4 oxygen on the right. So I'm going to need 2 waters here to balance the oxygens for that one. All right. But then step 3 also says now you use the H plus to balance the hydrogens. So in the first one, I see now 12 hydrogens on the right. So I'm going to have 12 H plus on the left. And then for the second one, I now see 4 hydrogens on the left. So I'm going to have 4 H plus on the right side. All right, so that was step 3. We used water to balance the oxygens, and then we're going to use hydrogen to balance the H, or use H plus to balance the hydrogens here. Now we need to use electrons to balance the charge. So in the first one here, I see 12 plus just from the hydrogen, but then there's a minus here, but then there's two of them, so that's 2 minus. So 12 plus 2 minus becomes 10 plus on the left side, all right? On this side, there's no charge, so it's 0. So I have 10 plus and 0 here. I essentially need them to balance here, all right? If I have 10 plus here, I need to get this side being 10 minus, all right? So when I do that, I'm going to have to add 10 electrons here to the right side, all right? So then what happens is we have 10 plus, now we have the 10 minus over here, the charge is balanced. I don't need the charges on both sides essentially to be equal here. Like I don't have to add the 10 electrons to this side to get 0 and 0. I should have some kind of charge on each side. So I need the 10 minus on this side. So I have 10 plus and then 10 minus here to cancel that out. And then if you notice, if that confused you, all right, you could easily just go to the second one here. If you notice in the second one, I see 2 minus and 4 plus here, which is 2 plus. The only way I can make that one work, all right, if this is 2 plus on the right, I would have to add 2e minus here to the left side. All right, that then gets you your 2 minus here and your 2 plus essentially canceling out. All right, so I do have my electrons now on opposite sides. This works. My charge is essentially balanced. So I've completed here step 4, but now I have to go on to step 5, which says get the common multiple, essentially get your electrons to cancel out. If I have 10 electrons in the top one and 2 electrons in the bottom one, I need to multiply the bottom one here by 5. So everything is going to get multiplied by 5. So that's going to get me 10e minus. I'm going to have 10 water now. I'm going to have 5 SO2, 5 SO4 2 minus, and then I'm going to have 20 H plus. All right, so now I'm ready to start totaling this up here and combining things, canceling from opposite sides. So obviously the electrons canceled out, which is what I wanted. But notice in this one, I have 12H plus on the top on the left and 20H plus on the bottom on the right. So that's going to cancel out all 12 of those. And this is going to become just 8H plus. And I can do the same thing with the waters. 10 waters on the bottom, 6 waters on the top right. They're on opposite sides here. So all of these waters are going to be gone, and the 10 is going to become 4. All right, so I canceled out what I could on opposite sides. Now I'm ready to total this up here. So when I do that, I get 4 water plus the 2 ClO3 minus plus the 5 SO2, and that's all my reactants, going to the 5 SO4 2 minus plus the Cl2, and then plus the 8 H plus that are remaining. All right, so I totaled everything up. If you need to check this here, you can confirm that you have equal amounts of each element on both sides and your charge is balanced. All right, now we can't stop here for this one because it said this needs to be in basic solution. So I have to do step 7, which says add OH minus to both sides to cancel out your H plus essentially. So I see 8H plus on the right, so that means I need to add 8 OH minus to both sides. All right, so I have 8 OH minus here on the left, and then I have 8 OH minus here on the right. Now that'll cancel out your H plus, but realize here it's not just going to make both of them disappear. It becomes water essentially. All right, 8 OH minus and 8 H plus become 8 water on the right side. But now be careful, you're not done yet because you had 4 water on the left that could cancel with the 8 water you just formed. So now all the water on the left side is going to be gone, and I'm going to have just 4 water on the right. So when we rewrite this here for our final answer, it's going to be 8 OH minus plus the 2 ClO3 minus plus 5 SO2 going to the 5 SO4 2 minus plus Cl2 plus the 4 H2O. So we had to do that last step with the OH minus here because it said it was in basic solution. But pay attention to that. You add the same amount of OH minus to both sides to make your H plus go away, but they become water, and you might have to cancel water on the other side as well. So this is, a pretty good example here of a redox reaction. Definitely need to know those steps. When you're writing your final equation here, obviously this entire thing is your final equation. You can write the reactants or products in any order, so don't feel like if you have to have the 8OH minus first or anything like that. As long as you have the correct amounts of the reactants on the reactant side and your products are on the product side, you're good here. You can have them in any order. So definitely be able to go through the steps of a redox equation here, being able to balance it. Let's look at another example here. We want to do this equation, balance this equation in acidic solution. So we have to follow our steps. We need to get to a point where we know those steps without even looking. First thing we need to do is write our half reactions here. So I'm going to pick one substance here on the reactant side. I see the MnO4 minus. It's going to be in a half reaction with the Mn2 plus. And then the Fe2 plus would be in a half reaction here with the Fe3 plus. Okay, so I have my half reactions. The second step says balance any elements that are not hydrogen or oxygen here. The Mn in the top one is balanced. The Fe in the bottom one is balanced. So we're good with that. Step 3 says we're going to use water here to balance the oxygens. So I see 4 oxygen on the top left. So I need 4 water here on the right. No oxygen in the second one. Then I'm going to use H plus to balance the hydrogens. So I'm going to need 8 H plus here on the left for the top one to balance the 8 hydrogens that are now on the right side of that one. All right, so now I took care of step 3. Step 4 says use the electrons here to balance the charge. I see 8 plus and the minus. That's going to be 7 plus total on the left side here. And I see 2 plus. 7 plus 2 plus. I need them to kind of be balanced here. So what I'm going to need to do, my only option for this one would be, because you can only add electrons, would be to add 5 electrons to the left side. All right, that'll make your 7 plus go down to 2 plus, which matches the other side being 2 plus. All right, so if I added my electrons to the top left, I know my electrons are going to be on the right side on the bottom. When I look at this, I see 2 plus going to 3 plus. So this is going to make sense. It's going to be pretty easy. It's just going to be 1 E minus here on the right side there. That makes each side 2 plus. Right? And I do have my electrons on opposite sides, so that's good. Now I'm at step 5, which says we need to make the electrons cancel. So we're going to need to multiply here. The top one is 5 electrons. The bottom one is 1 electron. This is easy. Just multiply the bottom one all by 5 to get the electrons to cancel. So it's going to be 5Fe2 plus, 5Fe3 plus, and now we'll have 5E minus. All right, remember, you have to multiply the entire half reaction by the number you need to make your electrons cancel. All right, now we are at step 6. We're going to cancel and add up. The electrons are the same on opposite sides here, one top left, the other one on the bottom right, so they cancel out. Remember, that's the point of getting the electrons to be the same so that they cancel. It doesn't look like anything else will cancel here. I don't have any common waters or H pluses that could cancel out. So I'm going to write what's left on each side. So I'm going to have, looks like 8H plus the MnO4 minus plus the 5Fe2 plus going to the 5Fe3 plus the Mn2 plus the H2O. And this is an acidic solution, so I don't have to do the OH minus step. This would be my balanced equation here. And you can confirm this. You can look at this and make sure that the elements match, all right, on both sides. For example, I see 8H plus here. I see 8 hydrogen on the other side, and you can check the charge and everything. All right, so there's no real reason why you should get these wrong if you're checking everything, but you do need to follow those steps, and you need to get to a point where you can do these equations, balance them from the steps in your head. All right, you need to be able to do it without looking at them. Here's another example that I want you to try. We want to do this equation in basic solution. All right, so you need to follow all the steps and make sure you can do this on your own. I would pause the video right now, try it, and then rejoin, and you'll see it solved. So pause the video right now. Hopefully, this is the answer you got, so check it carefully. You did have to be careful here. You got 2 electrons on the top one on the right side, and then you had 3 electrons on the bottom one on the left. Once you knew where the electrons went on the top one, you knew the electrons for the bottom one had to go on the opposite side here. But the only way they would cancel is if you got them both to be 6 electrons. So the top one had to be multiplied by 3, all of it, and the bottom one had to be multiplied by 2, all of it. When you cancel your electrons and, cancel out your waters and hydrogens here, you can see the equation you got, but because this was in basic solution, you had to add 2 OH minus to each side because of the 2H plus here on the left. But when you add the 2 OH minus to this side, it combines with the H plus to form 2 water. But be careful, there was a water here on the right side already, so this water would cancel with one of the 2 waters here. That's why your water is on the left side here. You still need that 2 OH minus though on the right. All right, so this is just another example of a redox reaction, and this one took place in basic solution. You got to know the steps here to do a problem like this.